In this video, we're taking some of the things that we've applied in previous lessons to have a conversation about symmetry. So you've probably heard of symmetry before, but you've probably only heard of one kind of symmetry. The symmetry most of you have probably heard of is what we call line symmetry or reflectional symmetry, where a figure can be reflected onto itself. But the definition of symmetry is just that any rigid motion can map the figure onto itself. So coming back to if a figure has line symmetry, naturally, if it does have line symmetry, there's going to be a line of symmetry. And in this lesson, they're talking about how you can use paper folding to see if there's symmetry over a line and to find that line of symmetry. So in this example, we are tracing the figure onto a piece of tracing paper. And it says that if the figure can be folded along a straight line so that one half of the figure exactly matches the other half, then the figure has line symmetry. So can I fold this triangle that I just traced basically onto itself? And yes, I can. And it says that the crease is our line of symmetry. And place your shape against the original figure to check that each crease is a line of symmetry. So if I take this figure and hold it here, and here, I'm looking at the same thing. And it says to sketch any of the lines of symmetry on this figure. So I know I've got one line of symmetry. Can I fold this triangle again so that it will fold onto itself? So let me try. Let me try folding it so it passes through this vertex of the triangle. So if I try to fold those two sides of the triangle onto each other, oh my goodness, I can't. So this figure has one line of symmetry. In this example, they're asking us to draw the lines of symmetry, if there are any, on each figure and tell the total number of lines of symmetry that the figure has. So in this rectangle, I can draw the line here. I can draw the line here. And there's frequently a misconception that you could draw it here, but you cannot. That won't fold exactly onto itself. This side is longer than this side. It's not going to fold onto it. So there's only those two lines of symmetry. Now this triangle, it doesn't say that anything is equal, but let me try tracing it. And checking to see, because I know I can't fold this side to land on this side or this side to land on this side, but maybe these two sides can fold together and form a line of symmetry. I don't know. Let's see. So it looks like it just might be. So if I fold it back up and put it on the figure, that looks good. And that looks good. So this does have a line of symmetry like this, but we've already discussed there would be no other line of symmetry. There's just that one. This L-shaped thing, again, I'm not 100% certain since nothing is marked as equal. So I'm going to trace it and maybe try folding it along here and see if it maps onto itself. And it does. So this has one line of symmetry. And in the first reflect question, it's asking a question that you may have already heard me answer. What do you have to know about any segments and angles in a figure to decide whether the figure has line symmetry? We need equal sides and angles. And what kind of figure has an infinite number of lines of symmetry? We'll consider a circle. I can draw, hopefully better than that, but I can draw infinite lines passing through the center of the circle. And all of those lines would be lines of symmetry. And this discussion question I think I'll leave and maybe post as a discussion question on Canvas. But I mentioned earlier that line symmetry or reflectional symmetry isn't the only kind of symmetry. We also have rotational symmetry. And so previously I said if a figure has line symmetry, naturally there is a line of symmetry. So if a figure has rotational symmetry, it would make sense that there would be an angle of that rotational symmetry. And you might want to bring out the highlighters here. The angle of rotation has to be greater than 0 but less than or equal to 180. Rotating something 360 degrees, we've talked about it before. Anything can rotate 360 degrees and map onto itself. That's not a big deal. It's when we're rotating something 180 degrees or less that the rotational symmetry of it becomes significant. In part A, we're taking this figure and tracing it onto tracing paper and turning it until it rotates onto itself. So here's my triangle. And there's the center of it. And I'm just in the interest of I'm going to take this triangle and rotate it until it lands on itself. And there, I've rotated it and it landed on itself. But you know what? Let me bring it back to where it was. Because notice that this top edge of my tracing paper, well, that's kind of a horizontal line. So when I turn my paper this far, I'd hope that you'd realize I've rotated it 90 degrees so far. So my angle of rotation is bigger than 90. It's less than 180. Okay, so I want to talk about what that angle is. Up here, they talk about how an angle of rotation is a fraction of 360 degrees. And here they're talking about how the angle of rotational symmetry for this 5-pointed star is 360 divided by 5. So maybe if I do 360 divided by the 3 sides that this triangle has, that's my degrees of my angle of rotation. I rotated that 120 degrees. And what are all the angles of rotation? Well, in this figure, because, and you can't see it very well on your screen perhaps, but you should be able to see it clearly on the paper and the textbook in front of you, all of these angles are marked as congruent and all of these sides are marked as congruent. So all of the angles of rotation are going to be 120 degrees. Here we're being asked if the figure has rotational symmetry. You might want to use tracing paper to verify, but this is a square. So all of the sides are equal, all of the angles are equal. If I were to take this square and turn it, eventually it would land on itself. So the math that I would hope that you see is you would do 360 divided by 4 in order to get a 90-degree rotation. And actually, the instructions are saying angles of rotation. So can I take that and rotate it something else that's not 90 but is still 180 degrees or less? Well, I'd hope that you'd see that yes, I can rotate it 90 degrees, but 180 degrees will also do the job. So I'm going to add 180 on that table. In this diagram, I'm asked if I can take this triangle and rotate it 180 degrees or less. And well, let's try it. So if I take this triangle, will I eventually map it on to itself if I'm turning it less than 360 degrees? No, I had to turn that paper a whole 360 degrees before it mapped onto itself. So none. And actually, let me come back to this square. It says identify all the angles of rotation less than 360. I don't know why it's asking that, but let's go ahead and make sure that we're answering their question. 270 will also work for the square. But again, I'm saying this with a bit of hesitance. The definition of rotational symmetry, remember, is that it has to rotate 180 degrees or less. Lastly, in this table, we're looking at this arrow. So maybe you want to trace it to check. Some of you might already have a guess that if I turn it 180 degrees, it will map onto itself. And the next question kind of comes back to a question we've already addressed. What figure is this next discussion question I do actually want to talk about. So it says I have a figure formed by line L and line M intersecting at 60 degrees. So I'm going to say that this is approximately 60 degrees. This is line L, and this is line M. And it's asking, does the figure have an angle of rotational symmetry of 60 degrees? Well, let's take tracing paper and test that. And while I'm tracing this, I'd like you to notice that if I called this 60-degree angle, angle 1, and this angle here, angle 2, they form a linear pair. And in the last lesson of Module 1, one of the things that was addressed in that lesson was that a linear pair, two angles basically adding up to a straight line, will add up to 180. So if I know angle 1 is 60 degrees, I know that angle 2 is 120. So I'm just kind of adding a little information into this diagram just in case you weren't already aware of it. So I'm going to take this figure and rotate it. Well, it's not mapping onto itself right now. And it's mapping onto itself now. And since I had to turn my paper 180 degrees, I would say, yes, it does have rotational symmetry, but it does not have rotational symmetry of 60 degrees. So actually, whoops, first question was, does the figure have an angle of rotational symmetry of 60 degrees? Not 60 degrees, 180 degrees. Continuing, we're describing figures and their symmetries. In example 1, they're asking us, draw the lines of symmetry, name the angles of rotation, or both if the figure has both. So example 1, part A, naturally they're kind of talking you through it. So it says, begin by finding the line symmetry in the figure. So look for matching halves. And matching halves comes in when you see a bunch of congruent segments. So notice, and again, you can't see it very well on your screen perhaps, but you should see it very clearly in your book that all of these segments are marked as congruent and all of these angles are marked as congruent. So that allows them to conclude that these are lines of symmetry. And it says, let's see if there are any more. So they noticed that if I cut it across the diagonal, that will also work. And then finally, they said look for some rotational symmetry. So thinking of the figure rotating around its center until it matches its original position. So since I've got all this stuff that's congruent to each other, and there's 4 points on this figure, then 360 divided by 4 is 90, and our angle of rotation is 90 degrees. Part B, in this figure, they're asking us to do the same, a little bit more on our own. So it says, look for lines of symmetry. One line divides the figure into left and right halves, so I can draw that line of symmetry. But I could turn it, and this would also be a line of symmetry. And so would that. Then look for rotational symmetry in step 2. Think of the figure rotating around its center until it matches the original figure. It rotates around a circle by a fraction of, well, how many points does this have? It has 3. And since these angles are all equal to each other and these segments are all equal to each other, then I've confirmed that 1/3. And 1/3 of 360 is the same as taking 360 divided by 3. It's 120. So find multiples of this angle to find other angles of rotation. So 120 will work, 240 will work, and then if I take 120 and multiply it by 3, that's 360, and 360 isn't significant. So let me pause a second. I clarified where the 120 came from up here. It's 1/3 of 360. The 240 is just a multiple of 120. It's 120 times 2. The number of lines of symmetry I covered up here. There's 3 of them. Finally, a couple more examples of describing the symmetry. So I'll do a couple of these, and then I'll leave figure 8 as the your turn. In number 6, this is a square again. So types of symmetry, I know it has line symmetry if I could draw. So it has line symmetry. And I know that I could also rotate this figure 90 degrees, 180 degrees, and 270 degrees. It is also asking for the number of lines of symmetry. So there's 1, 2, 3, 4. Number 7, the types of symmetry. I can see the line already drawn in, so this has line symmetry. But if I rotate that anything less than 360 degrees, it will not map onto itself. So I'm going to say not applicable here. And the number of lines of symmetry that this figure has is just 1. Pause your video and work through the your turn below, number 8.